There's this moment that comes when you're studying astrophysics professionally, when suddenly the abstract becomes concrete. When the equations on a blackboard, when the data in spreadsheets, when the theoretical models suddenly become real events happening in the sky above us. When the theories you've been learning about and teaching for decades suddenly crash into the real world with the force of billions of tons of plasma traveling at millions of kilometers per hour. That moment came for millions of people on October 1st, 2026. Not because they were studying astrophysics. Not because they were paying attention to space weather forecasts. Not because they understood what a coronal mass ejection was or what a geomagnetic storm meant. But simply because their lights went out. All of them, at the same time, across a geographic area the size of a continent. Let me transport you back to that moment. I want you to imagine you're standing in a major metropolitan city. Let's say New York or Chicago or Toronto or Los Angeles. The autumn weather is pleasant. It's late morning. People are at work, conducting their business as usual. People are checking emails. People are attending meetings. People are making phone calls. Kids are in school, learning their lessons, using computers, typing on keyboards. The city is running on electricity like it always does. Like it always will, you think. Electricity is infrastructure. It's background. It's infrastructure. It's the invisible system that makes civilization run. You don't think about it. You don't notice it. It's just there. And then, in a matter of minutes to hours, that background fails. The power goes out. Suddenly, without warning, the lights go dark. The computers shut down. The elevators stop between floors, trapping people inside. The air conditioning stops running. The heating stops. The refrigerators stop working. The stoplights stop functioning. The entire electrical system that powers modern civilization suddenly stops running. The hospitals switch to generators. They sound their alarms. The alarm systems in the hospitals, the backup power systems, all switch on. Emergency rooms suddenly transform into zones of controlled chaos as medical personnel adapt to running on battery power and generator backup. Computer systems go haywire as the carefully managed electrical supply that they depend on is suddenly interrupted. All the monitors in the intensive care unit that were displaying vital signs go dark. Then the backup power kicks in and they come back online, running on battery and generator power. Police dispatchers talk into handheld radios because the cell networks are overwhelmed and then failing. The cellular towers that normally relay calls from millions of phones are running on backup power, and that backup power only lasts a few hours. After that, the towers go dark. Traffic lights go dark in entire neighborhoods, causing gridlock as drivers try to navigate without them. Stoplights become four-way stops, and intersections become chaos. Pedestrians try to cross streets with cars not stopping. Accidents happen. Water treatment plants go offline. Their pumps require electricity. Without that electricity, water can't be pumped through the system. Faucets go dry. People suddenly realize they don't have water. Toilets don't flush. But here's what people don't realize, what really matters, what the scientists know. You're watching the evidence of something extraordinary happening in space. You're watching the most dramatic demonstration of solar physics that has occurred in modern times. You're watching the consequences of our star, the sun, demonstrating its power to anyone paying attention. You're watching the sun assert its dominance over the electrical systems that sustain modern civilization. And if you were paying attention to the solar observatories in the days and weeks before that October date, if you were watching the data streaming in from satellites and ground-based instruments, if you were among the community of scientists who dedicate their lives to understanding the sun, you would have seen something remarkable. The sun was building towards something catastrophic. Something that nobody wanted to see, but everyone who studies the sun had been predicting. Let me explain how we got here. Let me take you back in time a few months, to the moment when scientists first realized what was coming. And let me explain why this event matters more than just a few days of blackouts. The sun has a secret. For most of human history, we didn't know it. We looked at the sun as this constant, eternal furnace in the sky. The sun rises. The sun sets. The sun warms the earth. It's simple. It's predictable. It's eternal. It's the backdrop against which all of human civilization has played out. It's the constant against which we measure change. We measure time by the sun. We measure the seasons by the sun's position in the sky. We depend on the sun for light and heat. Except it's not a constant. The sun is a dynamic system. It's a massive nuclear reactor with a mass of 2 × 10 to the power of 30 kilograms. That's 2 followed by 30 zeros. If you tried to write that number out, if you wrote a 2, then wrote a 0, then another 0, then another 0, and you kept going, writing a 0 30 times, you'd be counting to the mass of the sun in kilograms. That number is so large that it's hard to comprehend. That's more than 99.8% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, every speck of dust, every object orbiting the sun. All of that combined makes up less than 1% of the mass of our solar system. The sun is that enormous. And inside this incomprehensibly massive object, inside this ball of hot plasma that you can't even look at directly without damaging your eyes, inside this giant sphere of matter that contains enough energy to power human civilization for the next few billion years, there are forces at work that dwarf anything we've ever created. There are nuclear reactions happening at rates that are unimaginable. Hydrogen is being fused into helium in the sun's core. This process releases energy according to Einstein's equation E = mc². The mass difference between 4 hydrogen atoms and 1 helium atom, when multiplied by the speed of light squared, that constant of 99.9 billion, yields an enormous amount of energy. The sun is converting about 600 million tons of hydrogen into helium every single second. Every second. Not per year. Not per month. Not per day. Every second. That's a rate of conversion of hydrogen that's almost beyond human comprehension. That's enough energy to power human civilization, all of human civilization, from the smallest village to the largest city, all electricity, all heating, all transportation, all industry, millions of times over. And the sun has been doing this continuously for about 4.6 billion years. It will continue to do this for another 5 billion years or so, until it runs out of hydrogen in its core and begins to die, expanding into a red giant and consuming the inner planets. But the energy from this fusion process doesn't just shoot straight out into space in a straight line. It has to travel through the sun first. It's generated in the core, in the region where temperatures reach 15 million Kelvin. At that temperature, at that level of thermal energy, atoms are completely ionized. Atoms are stripped of their electrons. Nuclei are exposed. And these nuclei collide with such force and frequency that they fuse, combining together to form heavier elements. The energy is released in the form of photons and subatomic particles and heat. This energy radiates from the core, getting absorbed and re-emitted by particles in the radiative zone. Photons are absorbed by a proton, then re-emitted in a random direction. The photon travels a short distance and is absorbed again. This process continues, with photons taking what's called a random walk through the dense material of the sun's interior. On average, it takes a photon about 1 million years to travel from the core to the surface, making countless absorptions and re-emissions along the way. Eventually, the energy reaches the convective zone, where the material is less dense and less opaque. Here, the energy is transported not just by radiation, but by convection. Hot plasma rises toward the surface. Cool plasma sinks back down. The motion is turbulent and dynamic and complex. You can see the results of this convection in the photosphere, the visible surface of the sun. You can see granules, cells of rising and falling plasma that create a pattern that looks a little bit like the cells of a honeycomb. Finally, the energy emerges at the surface as photons that we experience as light and heat. The photons scatter from our atmosphere and hit our eyes and cause the sensation of brightness. They warm our skin and cause the sensation of heat. They grow the crops that feed us. They power the water cycle. They drive the weather. They are the source of almost all energy on Earth. Now, here's where things get complicated. Here's where things get interesting. Here's where things get consequential. The sun isn't just made of gas and plasma. It's made of gas and plasma that's permeated by a magnetic field. This field is generated by currents flowing in the sun's interior, in much the same way that a magnetic field is generated by an electrical current flowing through a wire on Earth. If you take a wire and wrap it around a magnet and run an electrical current through the wire, you create a stronger magnetic field. This is how electromagnets work. They're magnets that are created by electrical currents, not permanent magnets. The sun has something similar happening in its interior. Currents of plasma, flowing due to the convection that's moving energy from the center to the surface, create magnetic fields. These fields are twisted and wrapped and reinforced by the rotation of the sun. The sun rotates on its axis once every 27 days at the equator, but it rotates slower at the poles, once every 35 days at the poles. This differential rotation, this difference in rotational rate between the equator and the poles, is unique to the sun. On Earth, every part of the planet rotates at the same rate. But on the sun, different latitudes rotate at different rates. This differential rotation stretches and wins the magnetic field, amplifying it, concentrating it. The magnetic field is normally confined to the interior of the sun. But sometimes it emerges at the surface. When it does, it creates sunspots, those dark regions you might have seen in pictures of the sun, or directly if you've ever looked at a solar eclipse. A sunspot is dark not because it's cold, but because the magnetic field is holding the plasma away from the surface. The inside of a sunspot is actually still incredibly hot, around 4,000 Kelvin. That's hotter than the surface of any planet in our solar system. That's hotter than an electric furnace. That's hotter than molten lava. But the surrounding photosphere, the visible surface of the sun, is even hotter. It's about 5,800 Kelvin. So by comparison, the sunspot appears dark. It's like comparing a red-hot coal to a piece of charcoal that's glowing white. The white charcoal looks brighter because it's hotter. The temperature difference makes the sunspot appear dark, even though it's still extremely hot. Around these sunspots, magnetic field lines loop up and away from the sun, extending high into the solar atmosphere. Sometimes, a single sunspot has 1 or 2 magnetic loops. Sometimes, an active region has dozens of loops, creating complex patterns of magnetic field structure. Sometimes, these field lines cross each other. And when field lines with opposite orientations cross and reconnect, when they snap like rubber bands that have been stretched past their breaking point and suddenly released, the magnetic energy that's been stored in the field is released. The release happens fast, sometimes in just a few minutes, sometimes in a matter of seconds, and it's violent. This is called a solar flare. A solar flare is one of the most energetic events that happens on our sun. It's one of the most energetic events in the entire solar system. An average solar flare releases the energy of about 10 million megatons of TNT. To put that in perspective, the largest nuclear bomb ever tested, the Soviet Union's Tsar Bomba, had a yield of about 50 megatons. An average solar flare releases the energy of 200 Tsar Bombas, detonating simultaneously. The largest solar flares release the energy of 10 billion megatons. That's about 100 times more powerful than average flares. That's the energy equivalent of 10 billion nuclear weapons the size of the Tsar Bomba, detonating all at once, at a single location, on the surface of the sun, released in a matter of minutes. If an explosion of that magnitude were to happen on Earth, it would be recorded in instruments around the world. The seismic waves from the explosion would be detected. The blast would level everything for hundreds of miles in every direction. The mushroom cloud would rise to the stratosphere. But on the sun, the largest flares are just routine events that happen during solar maximum. They happen multiple times per solar cycle. And when a flare goes off, when that energy is released, it doesn't just emit light in the visible spectrum. That's a small fraction of the energy release. The majority of the energy is released in wavelengths that are invisible to our eyes. The flare floods the solar system with X-rays and extreme ultraviolet radiation, energy that would be completely invisible to our eyes but would be devastating to unshielded electronics and to human skin and tissue if it reached Earth at high intensity. It accelerates particles, protons and electrons and heavier atomic nuclei to speeds that approach nearly the speed of light. These are called solar energetic particles, or SEPs. These particles, moving at relativistic speeds, carry enormous amounts of kinetic energy. They can penetrate through the atmosphere of a planet. They can damage electronics. They can cause radiation sickness in unshielded humans. And sometimes, especially if the flare is large, especially if the energy release is particularly violent, especially if the flare occurs in an active region where the magnetic field is particularly twisted and tangled. The flare does something even more dramatic. It tears a hole in the sun's corona, that thin outer atmosphere that extends for millions of kilometers around the sun. It's one of the strangest features of the sun. The corona should be cooler than the surface. Heat flows outward, so the further you go from the heat source, the cooler it should be. But the corona is hotter than the photosphere. It reaches millions of Kelvin. It's paradoxical. Scientists are still working on fully understanding why the corona is so hot. But part of the explanation involves magnetic field lines that carry energy from the surface and release it in the corona. When a large flare occurs, when that energy release is particularly violent, it can tear a hole in the corona. When that happens, the material in the corona can escape. Not just a little bit of material, not a few million tons. Billions of tons of plasma get ejected into space at speeds that can exceed 4 million kilometers per hour. That's faster than the escape velocity of our solar system from the sun. These particles are being ejected with such force that they'll be traveling through space for the rest of their existence. This ejection of material, this launching of billions of tons of plasma into space, is called a coronal mass ejection, or CME. A CME is a truly awesome phenomenon. In the literal sense of awesome, inspiring awe and wonder and a sense of scale that makes you feel small. A CME is a bubble of plasma, twisted with magnetic field, hundreds of thousands of kilometers across, traveling through space at millions of kilometers per hour. The CME is not a solid object. It's a cloud of ionized gas plasma. It's mostly protons and electrons with some heavier ions thrown in. And twisted through this cloud is a magnetic field, stretched and tangled and under tremendous stress. To put the size in perspective, if the sun were the size of a basketball, a CME would be the size of a beach ball. And it's traveling through space at a speed that would carry it across the United States in about a second. Now, most of the time when the sun throws out a CME, Earth isn't in the path of it. Space is big. The sun is at the center, Earth is about 150 million kilometers away, a distance called 1 astronomical unit, or AU, and most of the CMEs that leave the sun don't travel in Earth's direction. But the sun throws a lot of CMEs. During a solar maximum, the sun might throw out a major CME every single day. With so many CMEs being thrown out, and with the geometry of space, with the sun's active regions distributed around the sun and rotating through different directions, sometimes one does point toward Earth. When one does point toward Earth, when the timing and the geometry line up just right, when the trajectory of the CME is aimed at our little planet, that's when things get interesting. That's when things get consequential. A CME takes about 18 to 24 hours to reach Earth, depending on how fast it's traveling and how directly it's aimed at us. During that time, scientists with access to satellites that are positioned between the sun and Earth can see it coming. Satellites like SOHO, the Solar and Heliospheric Observatory, which has been observing the sun since 1995. SOHO has cameras that can observe the sun in multiple wavelengths, and it can see CMEs being launched. When a CME erupts, SOHO's cameras capture images of the material being ejected. Or the Parker Solar Probe, which was launched in 2018 with the mission to get as close to the sun as possible and to measure the solar wind directly. It has repeatedly broken the record for the closest approach to the sun by a spacecraft. It orbits closer to the sun than Mercury does. It measures conditions in the solar wind and the solar atmosphere with unprecedented precision. When a CME is ejected from the sun, it has to pass by the Parker Solar Probe if the Parker Solar Probe is in the right position. The Parker Solar Probe can directly measure the CME's properties. Or the Discover satellite, the Deep Space Climate Observatory, which is positioned at the L1 Lagrange point, a special location about 1.5 million kilometers from Earth, in the direction of the sun. At this point, the gravity from the sun and Earth balance out, so Discover can orbit at a fixed position relative to Earth and sun. Discover has instruments that continuously monitor the solar wind. It's the first line of warning for space weather events headed toward Earth. When a CME is detected by these observatories, when scientists see the data that says a CME is coming toward Earth, they can issue warnings. They can tell governments and utilities and power companies, brace yourselves. Something big is heading your way. Here's when it will arrive, plus or minus a few hours. Here's how strong we estimate it will be. Here's what you should prepare for. Here's what could happen. This is where the story of 2026 really begins, where the narrative shifts from the routine observations of solar activity to the moment when scientists realized they were watching something big build, where the routine became extraordinary. In late September of 2026, the sun had been going through what solar scientists call a robust maximum phase. Since about 2024, the number of sunspots on the sun had been increasing steadily, as expected during the 11-year solar cycle. The 11-year solar cycle had reached its peak around this time. By September 26, there were dozens of sunspots visible every single day. Some of the active regions, the areas where sunspots form, were enormous. They were so large that you could see them without a telescope if you used the appropriate eclipse glasses, the special glasses designed to protect your eyes from the sun's radiation. The sunspots would appear as small dark spots on the sun's disk. You could watch them move as the sun rotated, carrying them across the disk. And here's something important to know. Larger active regions, statistically, produce larger flares and larger CMEs. It's like the difference between a small bonfire and a large forest fire. The larger the pile of wood, the bigger the fire it's likely to produce. The more magnetic field energy stored in an active region, the more energy is released when that field becomes unstable. The scientists watching the sun knew this. They were expecting something big. Models and predictions suggested that this solar maximum would be comparable to the maximum of 1859, the Carrington event, the largest geomagnetic storm in recorded history. Some models actually suggested that 2026 maximum might be stronger. The sun's activity was tracking to be one of the strongest in recorded history. And then, starting around September 25th, the sun delivered. It delivered exactly what the models had suggested it might. It delivered a demonstration of the power that a star can muster. The first major flare occurred on September 26th. It was classified as an X-class flare, where X is the largest classification for solar flares. X-class flares are given numerical ratings, typically ranging from 1 to 20 or even higher, with no hard upper limit. The one on September 26th was rated an X3.2. That's a powerful flare, one of the most powerful that happens during a solar maximum, but not the most powerful that could happen. That would be an X20 or even higher. What made this flare interesting to the scientists watching it was that it was clearly the beginning of something. The active region that produced it was full of potential. There was more energy stored in the magnetic field. Magnetic field reconnection events would trigger more flares. The pressure was building. This was not an isolated event. Within hours, another major flare erupted. This one was an X2.1, different part of the same active region. Different magnetic field configuration, different energy release. Then another flare. This one was an X1.8. By September 28th, there had been 3 X-class flares and dozens of smaller flares, all originating from a single active region. The region was tearing itself apart, magnetically speaking. Energy was being released in bursts, one after another, each one feeding the next like a chain reaction. Each flare would release some of the magnetic tension, but new field lines would emerge from below the surface, and the tension would build up again, eventually triggering another flare. And each time an X-class flare occurred, each time one of these billion megaton explosions happened on the sun, there was a high probability that a CME would be associated with it. That the flare would tear a hole in the corona and launch billions of tons of plasma into space. NASA's Solar Dynamics Observatory, a satellite that orbits Earth and observes the sun in unprecedented detail, captured extraordinary images of these eruptions. The SDO carries cameras that observe the sun in multiple wavelengths, from ultraviolet to extreme ultraviolet. In these images, you could see jets of plasma being launched into space, arcing away from the solar surface at speeds of thousands of kilometers per second. You could see the sun's atmosphere, the chromosphere and the corona, rippling from the force of the eruptions. You could see waves propagating away from the site of the eruption, like waves on the surface of a pond when you throw a stone. Except these aren't water waves. They're waves of magnetic energy and plasma, traveling at speeds of hundreds of thousands of kilometers per hour. These are called Moreton waves, and they're caused by the shock wave from the flare propagating through the chromosphere. The images showed the magnetic field being twisted and torn. You could see that the field was no longer in a stable configuration. It was chaotic. It was dynamic. It was releasing energy. The SOHO spacecraft, positioned at the L1 Lagrange point between the Sun and Earth, detected the CMEs as they began their journey toward our planet. SOHO has cameras that observe the Sun's corona and can see CMEs being launched. The images showed enormous bubbles of plasma, hundreds of thousands of kilometers across, rushing away from the Sun at speeds exceeding 2 million kilometers per hour. Scientists analyzing the images could see that at least 2 of these CMEs were headed roughly toward Earth. The trajectory suggested that they would hit Earth's magnetosphere within about 18 to 24 hours. And then something happened that made the situation more severe, more serious. A second major active region, located on a different part of the Sun, began producing large flares. Now you had CMEs coming from multiple locations on the Sun, all being launched within a few hours of each other. The implications were immediately clear to anyone who understood solar physics. Multiple major CMEs, arriving within hours of each other, would pummel Earth's magnetosphere. Instead of a single disturbance allowing the magnetosphere time to recover between events, there would be a cascade of disturbances. The magnetosphere would be in a state of constant turbulence. The energy input would be enormous. This was shaping up to be the worst geomagnetic storm in the satellite era. At the Space Weather Prediction Center in Colorado, operated by the National Oceanic and Atmospheric Administration, NOAA, an agency of the United States government that monitors solar activity and issues space weather forecasts, scientists were gathering around their consoles. They were running their models. They were calculating trajectories. They were assessing arrival times. They were reviewing historical data. They were consulting with colleagues at NASA and at universities. They were also confronting a decision, a difficult decision. The data was clear. The prediction was clear. Multiple major CMEs were headed toward Earth. A severe geomagnetic storm would result. But how certain were they? What was the uncertainty in their predictions? How should they present this information to the public, to utilities, to government agencies? Space weather forecasters face a constant dilemma. It's the same dilemma that meteorologists face when predicting hurricanes. If they issue warnings that are too alarmist, they risk causing panic and economic disruption. People might evacuate unnecessarily. Utilities might shut down infrastructure unnecessarily, causing economic losses. If they're too conservative, if they downplay the threat, they risk being wrong, caught off guard by an event they should have warned about. They risk not having enough time for people to prepare. It's a delicate balance. Too much warning, too much alarm, and people don't believe you the next time. The boy who cried wolf phenomenon. Too little warning, and when the disaster hits, you're blamed for not warning people. In the case of the 2026 solar storm, the evidence was overwhelming. The data was clear. Multiple X-class flares. Multiple CMEs. The velocities of the CMEs measured by SOHO and Parker Solar Probe. The magnetic field measurements from SCAVR. Arrival times suggesting that they would hit within 18 to 24 hours. The conclusion was clear. This would be a major geomagnetic storm. Not the absolute worst-case scenario, not a Carrington-class event by all measures. But close. Very close. Maybe the closest we'd come since we started monitoring the Sun with satellites in the 1970s. The decision was made to issue a severe geomagnetic storm watch. This is the highest level of warning they can issue. On the space weather scale, warnings go from minor to moderate to strong to severe to extreme. Severe and extreme level warnings mean that significant infrastructure disruptions are expected. The alert was issued to the proper channels. Official warnings were sent out. Utility companies were notified immediately through emergency notification systems. They began implementing emergency protocols. Engineers who had been trained to respond to space weather threats began their preparations. This wasn't a theoretical exercise anymore. This was real. This was happening. Transformers were disconnected from the grid to prevent damage from induced currents that might be caused by a geomagnetic storm. Power flow was reduced in critical areas. The grid was intentionally reduced to lower stress levels so that when the storm hit, it would hit a weaker system that was less likely to cascade into failure. Backup generators were checked to make sure they were operational. At hospitals, at data centers, at water treatment plants, at any facility that had backup power, the generators were tested. Fuel supplies were checked. The systems that would kick in if the main power failed were verified to be working. Personnel were put on standby, ready to manually manage the grid if computer systems were compromised or damaged. These grid operators knew what to do. They had trained for this. They had run simulations. Now they would put that training into practice. Airlines were notified about possible disruptions to radio communications and instrument navigation systems. Flights that normally passed over the polar regions, where the auroras would be most intense and the radiation environment most hazardous, were rerouted to southern routes or delayed until the storm had passed. The polar regions are where the space weather effects are strongest. Radiation levels are high. Radio propagation is disrupted. Autopilot systems can malfunction due to the radiation environment. So aircraft flying over the poles during geomagnetic storms can experience navigation problems. It's safer to route them differently. Satellite operators received warnings. Spacecraft that could be put into safe mode, a reduced power state that protects sensitive electronics by disabling non-essential systems, were switched over. The mode conserves power and protects the most critical systems. Most satellites have such a mode for emergencies. The military was briefed on potential disruptions to GPS and satellite communications. GPS satellites provide positioning information that's critical to military operations. If those satellites malfunctioned or were damaged, operations would be affected. Contingency plans were activated. Emergency services were alerted to prepare for possible outages. Police departments, fire departments, ambulance services, they were told to expect power disruptions. They were told to prepare their backup systems. They were told to be ready. The news media picked up the story. Headlines began appearing in newspapers and on websites. Major solar storm warning issued. Solar flares could disrupt power grid. Scientists warn of severe geomagnetic storm. The story was picked up by national news. It was trending on social media, and the general public began to worry. Some people were scared. They didn't understand what a solar storm was, but they understood that scientists were warning about something that could affect their lives. Some people were skeptical. Solar storms? That sounds like science fiction. Some people prepared. They bought supplies. They filled bathtubs with water. They charged their batteries. Some people ignored it entirely. See, here's the thing. Most people don't really understand what a solar storm is. They hear solar storm and they think of something like a hurricane, a visible phenomenon that you can see coming on satellite imagery, a system that has a clear structure and a clear path that you can track and predict. They don't understand that a solar storm is invisible. It's not like a hurricane. You can't photograph a solar storm with regular cameras. It's not a system of winds and clouds. It's a disturbance in the magnetic environment of space. It's energetic particles traveling through space at relativistic speeds. It's plasma in motion. It's magnetic fields being twisted and disturbed. So when people started reading news reports about a major solar storm coming, and they looked outside and saw that the sun was shining just like normal, that the sky was blue, that there were no dark clouds, there was a disconnect. Some people assumed the warnings were overblown. Others bought supplies and hunkered down in their homes, preparing for what might happen. There were even some people who believed the government was using the solar storm as a cover for some other event. There's always a conspiracy theory. Some people thought the government was testing some kind of weapon and calling it a solar storm to cover it up. But the scientists were serious. The data was clear. The storm was coming, and it would be intense. It would test the electrical infrastructure of the developed world. The first CME was set to arrive on the morning of October 1st, at approximately 4 a.m. Greenwich Mean Time. That's 4 in the morning Universal Time. The second would arrive roughly 12 hours later. There was some uncertainty about the exact timing. The predictions were plus or minus a few hours, and some uncertainty about the exact strength, but the trajectories were clear. The storm would hit. It was inevitable. October 1st arrived, And right on schedule, at a few minutes after 4 a.m. UTC, the solar wind monitor on the Discover satellite, the Deep Space Climate Observatory, also positioned at the L1 point about 1.5 million kilometers from Earth in the direction of the Sun, detected something. There was a sudden increase in particle density. The density of protons and electrons in the solar wind suddenly jumped. The velocity increased. That's the signature of a shock wave from a CME arriving. The leading edge of the CME, the shock wave, had reached Earth's orbital position. Alarms sounded at NOAA. Scientists who had been waiting for this moment, who had been monitoring the data constantly, suddenly had real data coming in. Not predictions. Real measurements. At first, from the measurements coming in from the data streaming from Discover, it seemed like it might not be too bad. The initial shock wave hit with what scientists would classify as moderate to strong intensity. The density increased. The velocity increased. But the readings weren't at the extreme end of the scale. Maybe this wouldn't be as bad as feared. Maybe the CME had weakened during its journey from the Sun. But then, as more data came in, as the magnetic field inside the CME arrived, things changed. Everything changed. The readings shifted. The instruments detected something new. The magnetic field that came with the CME was enormous. It measured about 1,000 nanometers in magnitude. For context, the average magnetic field in the solar wind is about 5 nanometers. The background level of the interplanetary magnetic field is usually around 5 to 10 nanometers. Sometimes it spikes to 30 or 40 nanometers during mild solar events. But this CME's field was 200 times stronger than normal. It was an enormous amplification. It was above the historical measurements for the satellite era. And crucially, the magnetic field was oriented in a specific direction relative to Earth's magnetic field. It was pointing southward, opposite to the direction of Earth's magnetic field at that location in space. This is important. This is crucial. When opposite magnetic fields meet, when you have one field pointing one way and another field pointing the opposite way, they can interact. They can reconnect. When they reconnect, they release energy. They allow charged particles to flow across the field line boundary. This is the mechanism by which the Sun's energy gets transferred into Earth's magnetosphere. This is called magnetic reconnection, and it's one of the most important processes in space physics. It's responsible for solar flares. It's responsible for what happens when solar wind magnetic fields interact with Earth's magnetosphere. It's responsible for the worst geomagnetic storms. On Earth's night side, in the magnetotail, the region behind Earth where the magnetosphere is stretched out by the solar wind like a windsock at an airport, magnetic field lines began to snap. Not all at once, but in cascading events. The snapping released tremendous energy, and it accelerated particles that spiraled down toward Earth's poles. The energy input was enormous. The rate of energy transfer from the solar wind to the magnetosphere exceeded all historical records. The KP index, which measures the intensity of geomagnetic storms, reached 9. The scale goes from 0 to 9, and it was maxed out. Within minutes, the aurora became visible. Not just visible at high latitudes in Canada or Scandinavia or Alaska, where auroras happen regularly during solar activity, but visible far, far south of the Arctic Circle. People in the northern United States, in Montana, in Minnesota, in Wisconsin, were seeing strange lights in the sky. The upper atmosphere was being lit up by particles flowing down from the magnetosphere, colliding with oxygen and nitrogen atoms, exciting them, causing them to emit light. In New York, the aurora was visible. Reports came in of people on the streets seeing green and red lights dancing across the sky. The colors ranged from green to red to purple. The lights danced and shimmered and waved across the sky. It was beautiful. It was awe-inspiring. It was a visible sign that something extraordinary was happening. But it was also a sign of danger. The magnetic disturbance was recorded by magnetometers at ground stations around the world. The readings were extreme. On the International Kindex scale, which measures geomagnetic activity from 0 to 9, with 9 being the most extreme, readings were reaching 9 for extended periods. The scale was maxing out. The needles on the analog meters were pegged at the maximum. The digital readouts were showing 9s over and over again. The magnetometer at Barrow, Alaska, which sits at the edge of the auroral oval, The region where geomagnetic effects are strongest showed readings that exceeded anything in the modern record. In power substations across North America, monitoring systems were sounding alarms. The changing magnetic field was inducing currents in long power lines. Faraday's law of electromagnetic induction, one of the fundamental laws of physics, was asserting itself. A changing magnetic field through a conductor induces an electric field. This is not theoretical. This is real. This is happening right now. Large transformers, which are essentially coils of wire wrapped around iron cores, which are designed to convert voltage up and down in electrical systems, were experiencing forces that threatened to destroy them. The induced currents were heating the windings. The insulation was being stressed. The protective systems were trying to disconnect equipment to prevent damage. The current flowing through a transformer that's been hit by a geomagnetic storm isn't a normal current. It's a DC current, a direct current. Transformers are designed to work with AC current, alternating current. An AC current alternates direction 60 times per second in North America. A DC current doesn't alternate. It flows in one direction continuously. DC currents can cause transformers to saturate, to reach their maximum magnetic flux. When a transformer saturates, the windings can overheat. The insulation can break down. And despite all the precautions, despite the preparations, some transformers failed. The first major failure was in Quebec, in Canada. A transformer at a crucial substation overheated and failed. This transformer was a critical node in the electrical network. Power that had been flowing through it had to flow elsewhere. The load was redistributed to other transformers downstream. Those transformers, suddenly carrying more current than they were designed to handle, also began to overheat. The protective systems were working correctly. They were doing what they were designed to do. They were disconnecting equipment before it could be damaged. But the consequence was that more and more of the grid was being disconnected. One by one, protective systems disconnected transformers from the grid to protect them from damage. A cascade of failures began. It started in Quebec and spread. Within hours, most of Quebec was without power. Over 6 million people in the dark. No electricity, no heat, no light, no refrigeration, no way to charge phones or laptops. The grid had failed. It was the evening when the power went out. People were at home or were trying to get home. It was September turning into October, so it wasn't brutally cold, but it wasn't warm either. People without heat were starting to feel uncomfortable. Failures spread to the northeastern United States. More transformers failed. New York, one of the most powerful and reliable electrical systems in the world, began to experience rolling blackouts. Areas with high electrical demand suddenly lost power. Times Square went dark. The iconic signs that illuminate the night suddenly went dark. People on the streets in Manhattan were suddenly in darkness, except for the lights of cars and emergency vehicles. In the Midwest, the Great Lakes region lost power in huge swathes. Chicago went dark. The lights of the city suddenly switched off. People in the streets were confused. People in their homes were wondering what had happened. Minneapolis went dark. Detroit went dark. Milwaukee went dark. Millions of people in the dark. Millions of people suddenly without electricity. Eastward, the blackout continued. The northeastern seaboard was mostly without power. In Washington, D.C., the capital of the United States, government buildings switched to backup power. Emergency services mobilized. The Pentagon maintained power. The White House maintained power. Critical government functions stayed online. On the West Coast, there were localized failures, but coordinated power management prevented a complete collapse. The Western grid, which had been better isolated and better prepared, held up better than the Eastern grid. But even on the West Coast, there were blackouts. Some areas experienced significant power disruptions, but the damage was contained. The grid didn't collapse completely. The cascading failures didn't continue indefinitely. You see, the grid operators, aware of the danger, had taken preventive action hours before the storm hit. They had manually isolated sections of the grid to prevent cascading failures. They had disconnected non-essential loads. They had rerouted power flows. It's the same principle as creating a fire break to prevent a wildfire from spreading. Firefighters will deliberately burn a section of land in a controlled way to remove fuel for the fire. When the main fire reaches that section, there's no fuel left for it to burn, so it can't spread further. Grid operators were essentially doing the same thing, but with electricity. They were removing load from the grid preemptively. They were isolating sections. They were preventing the cascade from spreading uncontrollably. Because of these actions, instead of a complete grid collapse, which could have taken weeks or months to recover from, which could have brought down hospitals, water treatment plants, food distribution networks, everything, they had instead coordinated partial blackouts. Areas were without power for hours, then days, but not weeks or months. The blackouts were contained. The damage was limited. Hospitals with backup generators kept running. Emergency rooms could still function. Ventilators could still operate. Operating rooms could still conduct surgery because the backup power kept the lights on and the equipment running. Patients on life support were safe. Most data centers, which had invested heavily in backup power to provide redundancy and resilience, kept running. The internet stayed largely functional. Emails could still be sent. Information could still be retrieved from the cloud. The digital infrastructure that modern civilization depends on kept functioning because it had been designed with backup power in mind. Emergency services adapted to the outages and kept operating. Police departments used their battery-powered radios. They managed to maintain communication and continue patrol operations, though many of their computer systems were offline. Fire departments were still able to respond to calls. Ambulances still ran. The communication systems that emergency services depend on had battery backup and were designed to operate even during power outages. This is because emergency services had learned from previous outages that they needed to have backup power for their critical communication systems. But still, millions of people experienced something they had never experienced before. They experienced living without electricity for an extended period. For many, it was the first time in their lives. For some, it was traumatic. For others, it was an adventure, a change from their routine. In the dark, without power, people began to understand something that's usually invisible to us. We live in an electrical civilization. Every aspect of modern life depends on electricity. Water pumps that bring water to your tap depend on electricity. Heating systems that warm your home depend on electricity. Air conditioning systems that cool your home depend on electricity. Refrigeration systems that preserve your food depend on electricity. Lighting systems that illuminate your home depend on electricity. Communication systems that allow you to call for help depend on electricity. Transportation systems that bring you to where you need to go depend on electricity. Medical equipment that keeps you alive depends on electricity. Every single one of these things requires electricity. When the power went out, people had to adapt. Some adapted well. People with generators, with solar panels and battery backup, with non-electric stoves and heating systems powered by natural gas or propane, they were fine. Hospitals with backup power were fine. Nursing homes that had prepared with backup generators could keep patients alive. But the vast majority of the population was suddenly living like it was a century ago. And it was uncomfortable. It was challenging. It was disorienting. An elderly person who depended on an electric bed to help them out of bed found themselves unable to get up. They had to ask for help from family or caregivers. A person with a CPAP machine for sleep apnea couldn't use it. They had to sleep without it, struggling to breathe. A person with an electric wheelchair couldn't charge it. They were trapped in their home or had to be carried. A person with diabetes who depended on a refrigerator to keep their insulin cool had to improvise, finding ways to keep the medicine at the right temperature in the dark. Emergency services responded, but the scale of the crisis was enormous. A region the size of several states was without power all at the same time. The demand for emergency assistance far exceeded capacity. Hospitals received more calls than they could handle. People with medical conditions suddenly had nowhere to go. In the dark, people gathered outside, sharing information, sharing food, sharing water. Communities that had become fragmented by technology and busy lives suddenly came together out of necessity. And then, About 12 hours after the first wave of the storm began to subside, the second CME arrived. By this time, grid operators had learned their lessons. They had seen what happened when the first CME hit. They knew what to expect from the second. They disconnected more of the system. They isolated more sections to prevent cascading failures. They prioritized critical infrastructure and shifted power resources to maintain service to hospitals, emergency services, and water treatment plants. But the second CME was more intense than the first. The magnetic field measurements reached the highest values that had been recorded in the satellite era. This wasn't Carrington-class by all measures. The Carrington event happened in 1859, before we had detailed measurements, but estimates suggest it was about 2 to 3 times more intense than this. But it was close. It was the closest we'd come since the 1859. The second wave of the storm caused additional transformer failures. But because the grid was already partially disconnected, because operators had been through this before and knew how to respond, the failures didn't cascade as severely as they might have. Power went out in additional areas, but the shutdown was controlled. The infrastructure held up, and after about 24 hours, the worst of the storm began to subside. The density of the solar wind decreased. The magnetic field returned to more normal values. The induction of currents in power lines decreased. Power restoration began, but it was slow, very slow. With the number of failed transformers, with the complexity of safely bringing large sections of the grid back online, you can't just switch everything back on at once. You have to do it gradually to avoid damaging equipment. It took days. Some areas had power restored within a day. Others took a week. Some transformer failures had to be resolved by actually replacing the transformer, which took weeks. The economic impact was immediately estimated in the tens of billions of dollars, possibly higher. Supply chains were disrupted. Manufacturers who depended on just-in-time inventory couldn't get parts because delivery trucks couldn't navigate the roads with no traffic lights. Factories had to shut down because they didn't have electricity. Hospitals reported shortages of medical supplies because deliveries had been delayed by the power outages. The stock market dropped sharply in the first few days after the storm. The markets dropped 15%. That's a huge decline. Investors worried about the long-term implications. They worried about how the economy would recover. They sold stocks. The market continued to fall. There were serious discussions about a potential depression, about supply chains taking months to recover, about food shortages, about the possibility that this crisis might plunge the world into economic hardship. But then something unexpected happened. The market recovered. Supplies were rerouted. Instead of waiting for the normal distribution networks to bring goods from manufacturers to stores, retailers worked directly with manufacturers. Goods were transported via alternative routes. In some cases, the government facilitated the movement of critical supplies. Manufacturers adapted. Factories that had been shut down brought in portable generators and resumed operations. Supply chains that had been disrupted found alternative paths. The economy proved more resilient than the initial panic had suggested. Within 2 weeks, most infrastructure was back to normal. Within a month, the economy had largely recovered. The immediate financial losses were eventually estimated at about $20 to $30 billion for North America. Significant, but not catastrophic. Not the multi-trillion-dollar impact that would occur if a true Carrington-class event, the most powerful possible geomagnetic storm, happened in today's world. Why wasn't it worse? Why did the economy recover relatively quickly? Why didn't we see the kind of long-term disruption that could have occurred? The reason it wasn't worse was preparation. Scientists had predicted the event. They had used decades of data about the sun's activity patterns to forecast that a major solar maximum would occur in the 2026 timeframe. They had warned that major events were likely. Grid operators had prepared. They had studied the history of geomagnetic storms. They had reviewed historical data about the Carrington event. They had understood what could happen, and they had taken steps to prepare. Engineers who had been trained to respond to space weather threats had practiced their protocols. They had run simulations. They knew what to do when the storm arrived. Because of these preparations, what could have been a civilization-ending disaster was instead a significant disruption. And that's the key lesson of the 2026 solar storm. It's not that the storm was weak. It was strong. It was one of the most powerful geomagnetic disturbances of the modern era. The magnetic field measurements during the second wave came close to the estimated strength of the 1859 Carrington event. But the induced currents in power systems, the main factor that determines the impact on electrical infrastructure, were actually comparable to or slightly larger than those estimated for Carrington. The reason this storm wasn't as damaging as Carrington would have been is that human preparation, human knowledge, human understanding of solar physics made the difference between disaster and disruption. If this storm had occurred in 1926, before we had electrical grids, the impact would have been unnoticeable. If this storm had occurred in 1986, when we had electrical grids but before we had detailed understanding of solar physics and before we had warning systems, the impact would have been catastrophic. But because it occurred in 2026, after decades of solar research, after the development of warning systems, after the implementation of protective measures, the impact was contained. Civilization survived. Now, let me tell you why this solar storm happened in the first place. Why did the sun choose October 2026 to lose its temper? The answer is that the sun didn't choose it. The sun doesn't choose. The sun doesn't have intentions or desires. The sun operates according to the laws of physics, and one of those laws is that active regions on the sun eventually become unstable. A sunspot forms when a loop of magnetic field breaks through the photosphere. This loop of magnetic field can store enormous amounts of energy, just like a compressed spring stores energy. The magnetic field lines are under tension. They want to straighten out. They want to reconnect. They're like rubber bands that have been stretched. They're trying to return to their relaxed state. Most of the time, the magnetic field remains in a stable configuration. The tension builds slowly. The active region grows. More magnetic field emerges from below the surface. More energy accumulates. But sometimes the configuration becomes unstable. The tensions become too great. The magnetic field can no longer support the stress. Something gives. The magnetic field lines snap and reconnect suddenly. When this happens, energy is released very quickly. In a matter of minutes or even seconds, the energy that's been building up for days or weeks is released all at once. A flare occurs. A CME is launched. The process is somewhat similar to the way earthquakes happen. The Earth's crust has stress locked into it. The tectonic plates are moving, but friction prevents smooth motion. Stress accumulates. Eventually, the stress exceeds the strength of the rock and it gives way. An earthquake occurs. Stress is released. Solar flares are similar. Magnetic stress builds in an active region. Eventually, the magnetic field can no longer support the stress. It snaps. A flare occurs. The trigger for this snapping can be subtle. It might be the emergence of new magnetic field from below the surface. It might be the shear between different parts of the magnetic field. It might be the way the active region is moving and rotating due to the differential rotation of the sun. Scientists have been studying solar flares for decades, trying to understand what triggers them, trying to predict which active regions will produce large flares and which will produce small ones. What they've discovered is that you can look at the characteristics of an active region, its size, its magnetic structure, its complexity, and estimate the probability that it will produce a large flare. But you can't predict the exact time with certainty. The magnetic field reconnection process is chaotic. There's turbulence. There are instabilities. There's a level of unpredictability built in at a fundamental level, which is why solar flare prediction is probabilistic. We can say, this active region has a 10% chance of producing an X-class flare today. Not, an X-class flare will definitely occur at exactly 3:47 p.m. In the case of the active regions that produced the 2026 storm, all the signs pointed to instability. Multiple CMEs had been produced in September. New magnetic field was emerging in the active regions. The complexity was increasing. The magnetic field structure was becoming more complicated. Scientists were saying that there was a high probability of more major eruptions. And they were right, but timing is always uncertain. The exact moment when the magnetic field will snap and reconnect, that's hard to predict. That's hard to forecast. This is why the Space Weather Prediction Center's warnings were phrased in terms of probabilities and timeframes. They said, "A severe geomagnetic storm will likely occur within the next 2 to 3 days." They couldn't say, "It will happen at this exact moment." But when it did happen, it happened at a particular moment, and it happened in a particular way that was largely unpredictable from first principles. This is something that people don't always appreciate about science. Science can't always predict exactly when something will happen, but it can predict that something will happen, and it can predict the probability, and it can understand the mechanism. And that's incredibly powerful information, because knowing that something will likely happen and knowing what the consequences will be allows you to prepare. The 2026 solar storm validated every prediction that had been made about the consequences of a major geomagnetic storm hitting Earth. It demonstrated how vulnerable the electrical grid is to geomagnetic disturbances. It showed that, even with preparation, significant disruptions are inevitable. But it also showed that preparation does matter. That having warning, having understood the problem, having taken precautions does help. The difference between disaster and disruption is preparation. And in the aftermath of the 2026 storm, an enormous amount of effort went into understanding what had happened and how to prevent similar disruptions in the future. Engineers reviewed how and why transformers had failed. They discovered that the induced currents had been even larger than the protective systems had been designed to handle. In response, plans were made to upgrade protective systems on transformers. New designs for more resilient transformers were proposed. Research was conducted into better understanding the mechanisms of transformer failure during geomagnetic storms. Grid planners studied how the cascade of failures had occurred. They modeled different scenarios. They identified points of vulnerability in the network where a single failure could cascade and take out large areas. In response, they designed ways to further subdivide the grid, creating what are called microgrids, smaller networks that can operate independently if the larger grid fails. Governments invested in stockpiles of replacement transformers. Because it takes months to manufacture a large transformer, and because only a few facilities in the world manufacture them, it's critical to have spares available. After 2026, countries around the world began keeping strategic reserves of transformers, just as they keep reserves of oil or other critical resources. Scientists at universities and research institutions received increased funding to study solar physics and space weather. New satellites were built and launched. Earth-based observatories were upgraded. International collaborations that had been discussed for years were finally funded. This is the positive outcome of the 2026 storm. It was a disaster, but it was a disaster that happened when we had enough technological advancement to understand it and prepare for it. If a solar storm of this magnitude had occurred 100 years earlier, before we understood solar physics, before we had the technology to observe the sun in detail, before we had warning systems, the consequences would have been unimaginable. The blackout would have lasted for weeks or months. Supply chains would have collapsed. People would have starved. The death toll would have been in the millions. But by 2026, we had the knowledge. We had the warning systems. We had decades of data about the sun's behavior. We had the technological capability to understand what was happening and to respond to it. This knowledge, this preparation made all the difference. Let me talk about what happens when a geomagnetic storm hits Earth in more detail, because this is the real story of why the storm had the effects it did. Earth has a magnetic field. This field is one of the most important features of our planet. It's invisible, intangible, but it's essential to life. This field is generated by motion in Earth's liquid outer core. Iron and nickel, swirling in the outer core, create electrical currents. These currents generate the magnetic field that surrounds the planet. The magnetic field extends outward from Earth, creating what's called the magnetosphere. This is a region of space surrounding Earth where the planet's magnetic field dominates. It's not a solid sphere. It's a dynamic system, constantly changing and evolving. The magnetosphere extends outward from Earth by about 60,000 kilometers on the sunward side. That's a distance comparable to the distance from the Earth to the Moon. The magnetosphere extends much farther on the night side, stretching out to distances of over 1 million kilometers. This sphere of magnetic field surrounds Earth and protects us from the solar wind. Without this magnetosphere, the solar wind would interact directly with Earth's upper atmosphere. It would strip away the atmosphere over time. It would bombard the surface with radiation. Life as we know it couldn't exist. The solar wind is the constant stream of charged particles flowing out from the sun. It's not a gentle breeze. Even on a quiet day, the solar wind is traveling at about 400 kilometers per second. That's almost 1,000,000 miles per hour. That's fast enough to travel from the sun to Earth in about 4 days. The solar wind pushes on Earth's magnetosphere. On the side facing the sun, the magnetosphere is compressed. On the opposite side, it's stretched out into a long tail, like a windsock at an airport, or like a comet's tail being blown by the solar wind. The magnetosphere is constantly being pushed and pulled by the solar wind, but it holds its shape, creating a bubble of protection around Earth. When a geomagnetic storm hits, when a particularly dense and fast solar wind hits the magnetosphere, the compression becomes extreme. The front of the magnetosphere, instead of being at its normal distance of about 60,000 kilometers from Earth, gets pushed inward to maybe 30,000 kilometers or less. The pressure increases tremendously. The magnetic field gets twisted and compressed and distorted. And then, in the magnetotail, the stretched-out region on Earth's night side, something dramatic happens. The magnetic field lines that have been stretched and twisted suddenly snap and reconnect. They snap like rubber bands that have been stretched to the breaking point and then let go. When magnetic field lines snap and reconnect, they release energy. All the energy that's been stored in the stretched magnetic field is released in a process called magnetic substorm. This energy accelerates charged particles. These particles spiral along the magnetic field lines toward Earth's poles. They're moving at very high speeds with very high energies. When the particles reach the upper atmosphere, at altitudes of around 100 to 400 kilometers, they collide with oxygen and nitrogen atoms. These atoms are excited by the collisions. Their electrons jump to higher energy levels. The atoms are no longer in their ground state. They're in excited states. When electrons fall back down to their normal, lower energy levels, they emit photons of light. The light is emitted in specific wavelengths corresponding to the energy difference between the excited state and the lower state. The light from oxygen atoms, when it falls from the excited 2D state to the 2P state, is green light at a wavelength of about 558 nanometers. That's the classic green color of the aurora. When oxygen atoms fall from even higher excited states, they emit red light. The light from nitrogen atoms is typically blue, at wavelengths around 400 to 425 nanometers. When nitrogen atoms are at very low altitudes, they can emit red light too. This combination of colors, this dance of light particles, is the aurora. The northern lights, the southern lights. The aurora is beautiful, but it's also a sign that something intense is happening in the magnetosphere. The aurora is visible when the particle flux is strong. During a mild geomagnetic storm, auroras might be visible at latitudes of 60 to 65 degrees north or south. That would include Alaska, Canada, Scandinavia, and Russia in the north. During a major geomagnetic storm, auroras can be seen much farther south than normal. During the 2026 storm, auroras were visible as far south as the southern United States. People in Florida, in Texas, even farther south, reported seeing auroras. That's unprecedented in modern times. In Fairbanks, Alaska, people reported seeing the aurora overhead. In Toronto, Canada, the aurora was visible. In New York, people on the streets reported seeing strange lights in the night sky, but the aurora is just the visible sign of what's happening. Below the aurora, in the magnetosphere and on the ground, other things are occurring. The changing magnetic field is inducing electrical currents. Faraday's law of electromagnetic induction, one of the most fundamental laws of physics, says that a changing magnetic flux through a conductor induces an electric field and a potential difference across the conductor. Power lines are conductors. Long power lines, stretching for hundreds of kilometers across the landscape, are excellent conductors. When the magnetic field changes rapidly, a large potential difference is induced across them. The induced current doesn't come from the power being generated at a power station. It's not caused by the power generation process. It's induced directly into the power line by the changing magnetic field in space. It's the result of Faraday's law being applied to the power system. The magnitude of this induced current depends on several factors: the rate of change of the magnetic field, the length of the power line, the orientation of the power line relative to the changing magnetic field, the conductivity of the ground, and other factors. During a major geomagnetic storm, the rate of change of the magnetic field can be enormous. The magnetic field can change by hundreds of nanoteslas in a matter of minutes. That's an incredibly fast change. For a power line 100 kilometers long, oriented in the right direction relative to the changing field, the induced current can be hundreds of amps. Now, the electrical grid is designed to operate at certain voltages and currents. A transformer designed to operate at a certain current can be damaged if the current gets too high. The transformer heats up. The insulation degrades. If the current is high enough for long enough, the transformer fails. This is what happened during the 2026 storm. The induced currents exceeded the capacity of the protective systems, and transformers failed. Once a transformer fails, the power flow is disrupted. Power that was flowing through that transformer now has to flow through other routes. This can overload other equipment, causing a cascade of failures. This cascading failure is the real danger of a geomagnetic storm. Not that a few transformers might fail, but that those failures will trigger a cascade that brings down large sections of the grid. The reason the 2026 storm wasn't more catastrophic is that grid operators, understanding this risk, had manually isolated sections of the grid beforehand. They had accepted small, controlled blackouts to prevent large, catastrophic ones. It's the same principle as creating a fire break to prevent a wildfire from spreading. You burn a section of land in a controlled way to remove fuel for the fire, so that when the main fire reaches that point, it can't spread further. Grid operators were essentially doing the same thing. They were removing load from the grid preemptively, isolating sections, to prevent cascading failures. This is why preparation matters. Why understanding the problem matters. Without that understanding, without that preparation, the storm would have caused much more damage. The 2026 solar storm taught humanity a profound lesson. We live in a technological civilization that is intimately connected to the sun's behavior. Our power grids, our communication systems, our financial networks, everything we've built depends on a stable electrical environment. And that environment is not guaranteed. It's not stable on all timescales. When the sun loses its temper, as it did in 2026, we feel the effects. But, and this is the crucial point, we can prepare. We can understand. We can respond. That's the real legacy of 2026. Not a catastrophe, but a wake-up call. And a wake-up call that led to preparation, to increased understanding, to a more resilient civilization. That's what makes the story worth telling. In October of 2026, the sun reminded us of something we sometimes forget. We live on a planet orbiting a star. That star is powerful beyond measure. And we, in our small way, have the capacity to understand that star and to prepare for its power. The solar storm of 2026 was not the worst-case scenario, but it was close. And in its closeness, in the way our civilization was tested and passed the test, we see a blueprint for the future. A future where we continue to invest in understanding the cosmos around us. Where we prepare for hazards that are rare but possible. Where we use knowledge and cooperation to protect ourselves not from the cosmos, but from ignorance about the cosmos. The sun will erupt again, probably in the next few years, definitely within the next couple of decades. When it does, we'll be ready. We'll watch it come. We'll understand what's happening. We'll prepare. We'll survive. And we'll learn more, adding to our knowledge, improving our preparation, making our civilization more resilient with each event. That's the promise of science. That's the power of understanding. That's what makes us, in the end, not the victims of cosmic events, but the masters of our own fate. The 2026 solar storm proved it. And in proving it, it gave us hope. Hope that, as long as we keep studying, keep learning, keep preparing, we can safely exist in this cosmos. Not protected from the cosmos, but living wisely within it. That's the real story of the solar explosion of 2026. and it's a story worth remembering. The sun showed us its power in 2026, and we responded by deepening our understanding of it. That's science. That's progress. That's humanity at its best.